Greetings. So today we'll continue with our lessons, and today actually we get to talk about the precise limit definition of a limit. Because remember we started first talking about giving the intuitive definition of a limit. So basically just trying to generalize the idea of a limit. That's why we use the tables and trying to show actually that when x is approaching some number, y gets to approach a certain number, or we can make y to be as close as we want to a certain number as much as x gets closer and closer to some other number. And on our second lesson, we got to use actually the limit laws. Actually, when you go to try to calculate limits without using a calculator, and actually we started again to talk about the asymptotes, actually defining that it's not always the case that when x gets closer to some number, y also get close to a certain number. Sometimes x can get closer to some certain number and y just gets to either increase without bound or decrease without bound, going to infinity or going to negative infinity. And that's what the previous class was about. So right now we're going to talk about the precise limit or precise definition of a limit. When we say actually L is a limit of f of x, what do we mean? And because we need to stop saying that as f of x gets close to L, because that's vague. It's not precise. That's not mathematics. Because I mean, the word close is a relative word. How close is close? Who determines that something is close, right? I mean, for example, you could be close to your friend and your significant other, your boyfriend or girlfriend can be say that you're too close, and you could feel different, like, but yes, you're close, but we're not that close. And the other person will feel like, no, you guys are close. So the word, okay, sorry for that example. But otherwise, my point is the word close is relative. So we need to come up with a mathematical way and stop using the word close. And that's what the lesson thereof today is about. And we actually get to get closer or get to learn more on absolute values. So let me share the notes so that we can jump into it. So, but basically what we're doing here, we are revisiting the first lesson and actually getting to come to a precise definition of a limit. Okay, I'm going to switch off my camera here because I want you to concentrate and not concentrate on this beautiful face of mine. I know I'm very, very handsome, but today it's about the class. We had to talk about the precise definition of a limit. So if you don't mind, I'm just going to switch off myself so that we can jump into this thing. Okay, let's go. Remember that the time we're talking about the intuitive definition of a limit. This is the definition that we gave, and we said suppose to generalize things, and we suppose that f of x is some function and is defined when x is near a. Remember we said x being near a, we mean that actually x is defined in some open interval containing a. We don't really care if it is defined at a, but we're just talking about some interval around a. And we introduced this notation saying that the limit of f of x as x gets closer to a is equals to L. And by this, we meant that the limit of f of x as x approaches a is equals to L. Or we said that actually f of x can become closer to L as much as we want by just taking the values of x to be as closer to a as we want. We remember again, we said we don't care what happens at a, so we're not talking about x is equals to a, we're talking about x being closer to a. But now, like I said, we can't talk about the word close because the word is very vague. So what we need to do right now, because remember that we need to prove, right? Because in mathematics, we don't talk about, I feel that you guys are close. Those things are psychology and social work. Those are the people that have to base their decision on looks or on whatever. But in mathematics, we need to prove. So when we say that L is a limit of f of x, we should be able to prove. You know, one of the things that is beautiful about mathematics is that even when you guys don't speak the same language, I mean, the person could be speaking Russian and not knowing English, or otherwise talking Chinese, and you're all in the same room, but you guys want to talk about some certain mathematics. You know, once you write the mathematics on the board, all of you guys can agree or can disagree. So basically, a mathematics is a language. So basically what I'm trying to say here is that we need to come up with a way of being able to define or being able to agree and not talk about closeness, because closeness is a relative word. So basically what we need to come up with a precise definition of a limit. That basically what do we mean when we say that L is a limit of f of x? So that's what this lesson will be about. For example, in order for us to be able to prove that the limit of x cubed plus cos 5x over 10,000 is 0.001, or the limit of x sine x over x when x gets closer to 0 is equal to 1, we should be able to prove. And it's not always the case that for us to be able to prove, we have to take out a calculator, draw graphs. We should be able to prove mathematically, because it's not always the case that you know how the function looks like. Like, for example, this function of x cubed plus cos 5x all over 10,000. I'm not sure how this function looks like. But otherwise, for us to be able to prove that these are the limits, then we need the precise definition of a limit. What do we mean by that? Okay, let's jump into it. Let's take, for an example, we have a piecewise function here, f of x. Remember, piecewise, I said, is a function that is defined by more than one function, right? So we have a straight line here, 2x minus 1, a polynomial. And again, we say that when so f of x is this straight line when x is not equal to 3, but at 3, the function is equal to 6. So intuitively, from what we said the last time, we said as x gets closer to 3 and not equals to 3, f of x gets closer to 5. And we use the notation and say the limit of f of x as it gets to 3 is 5. So this is what we have so far. But now we want to now investigate. So if f of x gets closer to 3, right? So now we want to work on this vagueness, or actually what do we mean when we talk about getting close? How close should 3 get closer to x such that f of x gets closer to 5 by 0.1? Remember we said the limit of f of x is the limit of f of x is 5 as s goes close to 3. But now we want to break that down or work in reverse and say that actually for the distance between f of x and 5 to be less than 0.1, how closer x should get to 3? That should be the question now. So basically, remember that the absolute value means distance. So basically, the distance from x to 3 is represented by, or is written as the absolute value of x minus 3. Remember, the absolute value, like I said, it wants the distance to be positive. So from the distance from 3 to x could be on the right-hand side of 3 or could be on the left-hand side of 3. But otherwise, we want this distance to be positive. So that's why there's absolute value means. So same thing as the distance from f of x to 5, that distance also, we get to put in absolute value. So we want the distance to be positive. Because our problem is to find some number. Right? Remember we said we want the distance from f of x to 5 to be less than 0.1. And we asked actually how close x should be to 3. So suppose that number, we call it this symbol. This is pronounced delta. So basically, what we're saying that, so we want this number, delta, such that f of x, the distance between f of x and 5 is less than 0.1. If x minus 3 is less than delta. Remember that x is not equal to 3. So basically, remember our investigation or our problem is for f of x to be as closer to 5 by difference of 0.1, how close or what should be the distance between x and 3? and that distance we say is delta. So basically what we want to know what is this number delta. And please keep in mind or note that actually it means, because now if you have to guess delta, how many times are we going to guess such that the distance is less than 0.1? So it means actually this delta, it has to depend on this 0.1, right? So that we stop wasting time beating around the bush. But otherwise, we'll get into it and actually get to show you what I mean when I say actually this delta, it has to be dependent on 0.1. Because if we change the 0.1 and say make it 0.001, are we going to go around giving 10,000 guess so that this is true? So it means actually this 0.1, it has to be an input for this delta. But otherwise, like I said, we'll get deeper into details later on to explain what I really mean. Let's break it down. So remember that we said we want the distance to be zero, to be positive. Absolute value is positive. So for the fact that we say the distance is positive, it means actually there exists some distance. So definitely x cannot be 3. Because if x was 3, then we'll have 3 minus 3, which is equal to 0. But here we're saying that actually the distance from x to 3 is strictly greater than 0. Right? So basically it means what we have here, we can break it down to this line here. So we want the distance from f of x and 5 to be less than 0 if we have some positive distance from x to 3 that is less than delta. So in other words, it means actually this delta is a positive number. I hope that part is clear. Let's look at this. Let's guess. Let's guess by taking this 0.1 and just dividing it by 2. I'll explain later why I divide by 2, but otherwise we're just trying to guess. Because remember I said our guess, it has to be depend on this number. Otherwise, we're going to have millions and millions of guesses for us to be able to come up with this number delta such that the distance from f of x and 5 is less than 0.1. So let's take this 0.1 that is given and divide it by 2, and the answer is 0.05. So now we want to see if delta is 0.05, does it make 0.5, f of x minus 5 to be less than the distance from f of x and 5 to 5, will it be less than 0.1? So the distance from f of x to 5, meaning f of x minus 5, remember f of x, we said is a straight line when x is not equal to 3, and that straight line is 2x minus 1, so we can substitute f of x for its formula. So simplifying here, we end up having 2x because we have minus 1 minus 5, which is minus 6. So if 2x minus 6, we can take out the common factor, which is 2. We end up having x is less than 3, 2 times x minus the absolute value of x minus 3. Remember here, on our guess, we said, on our guess here, we said we are guessing our delta, and we said our delta to be 0.1. So we already said that actually the distance from x to 3 is less than 0.05. So meaning we can substitute that here. So it means actually because it's strictly, remember this is strictly less than. So if x minus 3, if 0.05 is greater than, or if x minus 3 is less than 0.5, so it means actually 2 times x minus 3 will still be less than 2 times 0.05. So multiplying these two, we get 0.1. So in other words, remember we started with the absolute value of f of x minus 5. So in other words, what we have here, we have that actually the distance between f of x and 5, or the absolute value of f of x minus 5, is going to be less than 0.1, right? So basically it means actually the distance from between f of x and 5 is going to be less than 0.1 if the distance between x and 3 is positive and is less than 0.05. So basically it means actually our delta is 0.5, and comparing with what we have here, it means actually our delta is 0.01 divided by 2. So meaning our guess was correct. But the question is, what if we want the distance between f of x or actually interpreting, let's finish first with what we have here. The answer to our problem is that if we choose our delta to be 0.0.5, that means that x is going to be within a distance of 0.05 to 3. If there's the case, or the distance between x and 3 is less than 0.05, then f of x is going to be within a distance of 0.1 from 5. Or the distance between f of x and 5 is going to be less than 0.1. But the question is, what if we want the distance, or we want f of x to be closer to from 5 with a distance of 0.01? Meaning we're changing that 0.1 to now to become 0.01. We can repeat the same process and say that let x be within a distance from 3 by 0.01. Meaning which is 0.005, right? Remember, I'm trying to push you somewhere here. You're not always going to need a calculator or need these calculations for you to come to that, to be able to choose that number. So please bear with me here. I'm trying to walk you somewhere so that you understand when we get there, how we got there. So basically it means in this case, as wanting the distance from f of x to 5 to be within a distance of 0.01. So in other words, if we divide this 0.01 by 2, it means actually the distance from f of x to 5 is going to be less than 0.01 if distance from x to 3 is positive and it's less than 0.005. I hope that is clear. And we can continue this process. If we want the distance from f of x to 5 to be less than 0.001, it means we need to make the distance from x to 3 to be to be positive and to be less than 0.005. I mean 0.005. So we can continue like this and like this. But now the question is, how can we generalize this? We want to generalize this so that we don't keep on using calculators like this. So, because remember, we want to come to that point whereby we can say that 5 is a precise limit of f of x as x is approaching 3. And not saying that actually, if it's within this distance, then we need to make x to be this close. We don't want to do what we just did here. So we want to generalize and say that if the distance between f of x and L is within this distance, say some letter or some within a distance A, then distance between x and, okay, maybe let me not use A. But otherwise, the point is we don't want to use precise numbers. We want to generalize this and just come up with symbol. So, let's say, because remember we said f of x, if L is a limit, then it means that the difference between f of x and L has to be less than some certain number, or for it to be less than some certain number, then x needs to be so much close to its to some point. So in other words, to generalize, if maybe we introduce this Greek letter called epsilon. So basically, we're going back to our question. For f of x to be as closer to 5, or for the difference between f of x and 5 to be less than epsilon, how much should x be closer to 3? Remember, we said actually how for x to be closer to 3 by some, we said we need to make x to be closer to 3 by some letter delta. And in our previous example, actually delta had to take this epsilon divided by 2 for us to be able to get delta. So in other words, delta was a function of epsilon. Because like I said, for us not to have millions and millions of guesses, for us to be able to get the difference or the distance between f of x and 5 to be less than some number. For us not to guess this epsilon, we said actually, sorry, this delta. So we said actually we need this delta to be closer to epsilon. I mean, we need x to be closer to 3 with a distance of epsilon. So basically, in the previous example, it means actually delta was dependent on epsilon, and in this case was actually epsilon over 2. I hope you are still with me. Let's try to break it down. So basically, this is the precise way of saying that f of x is close to 5 when x is closer to 3. So it means actually if f of x, the difference between f of x and 5 is within some distance epsilon or within epsilon, that can only be true if the difference between x minus 3 is positive and is within or is less than delta. So this actually, it means actually we can make the values of f of x to be as closer to be within a distance of epsilon from 5 by just taking the distance or the values of x to be within a distance of epsilon over 2 from 3. Remember this epsilon over 2, it comes from, we're talking about the example that we just used. It's not general. It's not always the case that we're going to divide by 2, but we just, from the example that we just did. So meaning x needs to be within a distance of epsilon over 2. So because for us, because remember we've been saying that we want the distance to be within 0.1 or to be a distance of 0.001, just like that. So that's why in our previous case we needed this epsilon to be over 2 for 5 to be a limit of f of x. So in other words, remember, okay, let me try to see if I can write here to explain where does this come from and what it means. But otherwise, this comes from the phrase that we just used. So remember we said if x minus 3 is less than delta, we said if x, the distance between x minus 3, this is 3, if the distance between x and 3 is less than delta, then the distance between f of x and 5 is going to be within a distance of epsilon. So basically, if here, remember that absolute values, it means, remember we want the distance around 3. So in other words, it means that we want the distance from 3. Remember we said it could be positive, it could be negative. So this, the distance from x minus 3 could be less than epsilon, or could be on the right, left-hand side of 3 and be within a distance of minus epsilon. So if we add 3, throughout, because remember we are adding, so the inequality sign does not change. So if we add 3 throughout, so it means actually we end up having 3 minus epsilon, of which is what we have here. So minus 3 plus 3 cancel out, you just left with x, here it is, and here we have epsilon plus 3, which is what we have here. So in other words, to rephrase what we just said, we said if x is within or is between 3 plus epsilon, 3 plus delta and 3 minus delta, then f of x will be within the distance of 5 plus epsilon and 5 minus epsilon. In other words, f of x is to be close to 5, and if we take x to be within an interval around 3, if we try to use graph, or if we use graph to explain what we just did here, let me erase what we have here so that this part, I want to erase it so that it doesn't disturb the graph, so that I can explain exactly what we've been saying here. I love the song. Okay, I think you guys can see. Let me go back to my pen. So basically we are saying that if x is in here, meaning it's around 3, and when I say around 3, it means if x is between, it's around 3, meaning it's within the boundary of 3 plus delta and 3 minus delta, meaning around 3, then f of x, it will be around 5 within a distance of 5 plus epsilon and 5 minus 5 minus epsilon, meaning for f of x, remember f of x is y within the straight line. So for f of x to be closer to 5, we need x to be close and closer to 3. So meaning when you close this bound, this interval here, when we make it to be smaller and smaller, then this interval around 5, it gets to be smaller as well. I hope that part is clear. So let's try to see if we can generalize this and come up with a definition. Remember, this is now the precise definition. It's not intuitive. We're not trying to be vague. We're trying to be precise so that we can be able to prove that the limit exists or and what is the limit. So because we're generalizing, let f be some function, and that is defined on some open interval that contains the number a, except possibly at a. It means actually we want f to be defined around a, right? Then in that case, we can say that the limit of this f of x, right, as this x is approaching a, it's L, right? Or we can say the limit of f of x as x approaches a, it's L, if for every, this is very important, if for every number, epsilon that is positive, there is a number called delta that is also positive, such that if x and a, the distance from x and a is less than delta, then the difference between f of x and L, or the distance from f of x to L, it will be less than epsilon. So remember, this is an if then. So if x is close to a, then f of x will be close to L, right? That's what we said that time when we're talking in vague terms. So right now we're saying that if the distance from, if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L will be less than epsilon. I hope that is clear. So if this is the case, then L is the limit of f of x. So basically, we can say that this is how we define a limit. Let's try to break it down again. Remember, the absolute value is the distance. The absolute value of x minus a is the distance from x to a, or the distance between x and a. And the absolute value of f of x and L is the distance between f of x and L. And again, epsilon and delta, they're just some numbers that are just, there's nothing special about them, or they are not specific numbers, but they're just arbitrarily some small positive number. So arbitrarily small numbers, right? So, and again, remember our notation, it means actually, if for us to say the limit of x or x, the limit of f of x as x approaches a is L, it means actually the distance, right? We're breaking down now, wanting to use these absolute values. The distance between f of x and L, right, can be made arbitrarily small by taking the distance between x and a to be very sufficiently small, but not equals to 0, because if it's 0, it means actually x is equals to a. So we want the distance from x and a, or x to a, to be sufficiently small. So let me repeat again. F of x can be made closer to L by taking the distance between x and a to be also very small, right? That's what we said when we were talking, explain limits intuitively. So in other words, now if we want to use this absolute delta definition, we can say that f of x, the limit of f of x as x approaches a is equal to L. It means that the values of f of x can be made to be as close as we want to L by making the values of x as possibly closer to a, right? That's what we still explaining what we know so far. So we said f of x can be made closer to L by taking or making the values of x to be closer to a, right? Now let's break it down. Now we want to use intervals. Remember we said that the distance, the absolute value of x minus a being delta, break it down using the intervals, it means actually x minus a is within the, is less than delta or minus, if a is on the left hand side, or if x is on the left hand side of a, it means the distance is positive. If a, we say that a is a bigger number, then the distance will be positive. But otherwise, if a is less than x, so meaning we're going to have a negative distance, which is minus delta. So we want to reformulate our definition. So remember that the absolute value of x minus a is less than delta. This is equivalent of saying that x minus a is between delta and minus delta, right? And from here you can add a across. If we add a across, so we're going to have minus delta plus a, which is same thing as a minus delta. Then minus a will cancel with the a, and on the far right you have delta plus a. So basically this comes from just adding through all out on all these sides of inequalities. And again, we said, remember that for the fact that you want the distance to be positive, it means that actually x cannot be equal to a. And again, same thing with the our limits. So basically f of x being less than, f of x, the distance from f of x to L, or from L being less than epsilon, it means actually L minus epsilon, or f of x is between L plus epsilon and L minus epsilon. Now, let's get to the definition. So the limit of f of x as x approaches a being equals to L, it means that actually for every epsilon greater than 0, irregardless how small, right? How small epsilon is, we can find some number delta that is also positive, such that if x lies within some interval, right, around a of delta, and x is not equal to a, then f of x will also lie within some open interval around I of epsilon. I hope that is clear. So for us to say that the L is the limit of f of x as x approaches a, we mean that actually for every, regardless how we want f of x to be close to L, regardless of the distance. So L can be as close as we want, or for every distance that is positive, or for every epsilon that is positive, we can find some delta. If we can find some delta that is also positive, such that if x is in some interval, a minus delta, a plus delta, right, within this interval, then we can also find f of x to be also in the interval of L minus epsilon and L plus, then in that case, L is the limit. That's how we get to prove that the limit exists, or L is the limit. So in other words, if x is in some interval of a plus delta, a minus delta, then f of x will be within some bound of L minus epsilon and L plus epsilon. So if this is the case, x is within this, then f of x will be between that. Then that case, L is a limit of f of x as x gets as x gets closer to a. In other words, so let's try to break it down, because this is very important for you to understand. If you want f of x to be close to L, then you need x to be closer as possible to a. So basically, this is what we mean. So for f of x to be closer to L, meaning if you want this interval, right, this blue area here, if you want it to be smaller, meaning if you want f of x to be close and closer to a, we just need to close these boundaries here around a. So if we close the boundary, the interval around a to be smaller and smaller, it means actually the interval around L, as it gets to be closer, it becomes also smaller and smaller. So that's what the delta epsilon definition means. Let's see if we can't use it. Let's see if we can use it to prove that the limit of x, the limit of 4x minus 5 as x approaches 3 is equals to 7, right? So you don't want to use a calculator to prove that it's true. We don't want to use limit loss for us to be able to prove that this is true. We want to use the epsilon delta definition. So now, so basically remember that we need to guess the value of delta, right? And for us to be able to prove, guess this delta, we need to be given epsilon. Remember we said delta is a function of epsilon. So again, we want to find, the whole point is to find some number delta, which is dependent on epsilon, such that if the absolute value of x minus 3 is less than delta, and the distance is positive, then the distance or the absolute value of 4x between 4x minus 5 and 7 is less than epsilon. So our whole point is to find this guy here. And for us to find that guy, we use it by guessing. So basically we want to cheat the system. So as cheating the system, we start at the end. So let's start first by taking f of x minus L and see actually what distance does it become. So if we take f of x, which in this case is 4x minus 5, minus 7, so we have minus 5 minus 7, which is minus 12. So taking the common factor of 4, remember 4 is a positive number, so we can take 4 out of the absolute value. We end up having 4 times the absolute value of x minus 3. But 3, x is approaching 3. So in other words, it means actually whatever epsilon, remember we said f of x minus L, meaning the absolute value of f of x minus L is less than epsilon. So in this case, it means that for whatever epsilon that we choose, right, that will help us to choose our delta. So in other words, we said, remember, we want to find delta. That's the point. So if the absolute value of x minus 3 is less than delta, then remember from what we have here, remember this is f, this was our f, and this was our L. So the absolute value of f minus L, it became less than, or was equals to 4 times x minus 3. So meaning 4 times the absolute value of x minus 3 can substitute it for f minus L. So meaning if x minus 3, if the absolute value of x minus 3 is less than delta, then 4 times x minus 3, the absolute value of x minus 3 will also be less than epsilon. That is what we just discovered, or actually that is general. So basically, we want to find this delta. So, but remember, delta cannot be a specific number, but it's going to be some number that is dependent on whatever we choose for this epsilon. So we need to find some epsilon that is, some delta that is dependent on this epsilon. So in other words, if we choose our delta, so it means that the absolute value of x minus 3 will be less than epsilon over 4. Remember we said delta is dependent on epsilon. So if you choose delta to be epsilon over, sorry for that. If we choose that our delta to be, what am I writing? If we choose our delta to be epsilon over 4, then the distance of x minus 3 will be within delta minus 4. Remember this x minus 3, it comes from f minus L. So basically, if the delta, we choose delta to be epsilon over 4, then our f of x minus L will be within our epsilon. So in other words, because we can see that, then it means that actually we need to choose our epsilon, our delta that is dependent on epsilon to be epsilon over 4. So now we want to choose to see actually what we chose, does it work? So remember I said we start at the end for us to be able to make a good choice of delta. We need to make an intelligent choice. Otherwise, we're going to be beating around the bush, guessing different values. So we will go at the end to guess. Then after that, our guess, we come back to prove that our guess actually is correct. So remember that this epsilon is an independent variable. Remember we said f of x can be made closer to L if x is being closer to A. So we choose some epsilon that is greater than 0, then choose, we are given, for whatever epsilon that we are given, we choose delta to be epsilon over 4, such that if absolute value of x minus 3 is less than delta, then f of x minus 7 will be less than epsilon. So if we try to simplify that, f of x is 4x minus 5. So minus 7, simplifying that, we end up minus 5 minus 7 is minus 12. Factorizing 4, which is positive, we can leave it outside the absolute value. So it means actually if the absolute value of x minus 3 is less than delta, then remember this x minus 3 we already said is less than delta. So 4 times the absolute value of x minus 3 will also be less than 4 times delta. We already chose delta to be epsilon over 4. So we can substitute our epsilon there over 4. Obviously, the 4 cancel out and we're left with our epsilon. So to summarize, we said if the absolute value of x minus 3 is less than delta, then remember here we just said f minus L is less than epsilon. So I'm just trying to emphasize this absolute value. So to summarize, we said if absolute value of x minus 3 is less than delta, then the absolute value of f minus L will also be less than epsilon. So we have met the conditions of actually saying that L is the limit of f of x. So we can conclude that actually if the absolute value of x minus 3 is less than delta, then f of x minus 7 will be less than epsilon. And actually this is how the function looks like. And we can see around 3 here, that x gets closer to 3, the function gets closer and closer to 7. So basically our definition here, we can see it graphically here. So if since all this is the case, we can conclude by definition. Okay, this is, I didn't highlight properly. So since all we have these conditions, now we can conclude that actually the limit of 4x minus 5 as x approaches 3 gives us 7. Let's take another example here. So we want to prove that, I hope the previous example was clear. If it's not, please try to go through it again, or you can email me if you're really struggling. So on 7katleho3@gmail.com. So here we have to prove that the limit of x approaches 3 of x squared is 9. So remember, the first step is to choose delta that is dependent on epsilon. But for us to be able to guess, we go at the end, then come back. So let's look at exactly what are we saying. So remember that if whenever epsilon that we are given, right, we need to find some number delta that is greater than 0, such that if the absolute value of x minus 3 is less than delta, then the absolute value of x minus its limit, in this case is 9, x squared minus 9 will also be less than epsilon. This is where we want to reach. This is our goal, right? So for whatever given epsilon that is greater than 0, we want to find some number delta such that if the absolute value of x minus 3 is less than delta, then the absolute value of x minus 9 will be less than epsilon. If this is the case, it means actually the limit of x squared when x is approaching 3 is equals to 9. Actually, the same thing goes for one-sided limits, if you remember that we did the one-sided limits. But now, for us to be able to connect this x minus 3 and x squared minus 9, x minus 9, remember the difference of two squares. So if you factorize, we end up having x minus 3 times x plus 3, right? So remember that our delta, it has to be greater than x minus 3. So for that, for delta to be greater than x minus 3, it means actually the absolute value of x plus 3 and x minus 3 has to be less than epsilon. But now, because we only, not that we only, but otherwise, this is our focal area, x minus 3, because that's why we get it. Because if that's the case, then we'll be sure that the epsilon, it satisfies our initial condition that actually the absolute value of x minus 3 is less than delta. So remember that x plus 3, remember the distance is positive. So we can say that, suppose that x plus 3 is less than some number c. We don't know what is that, but otherwise we say that actually the distance from x, the absolute value of x plus 3 is less than c, right? And that c is a positive number. So in other words, it means actually multiplying the two absolute values of x plus 3 and x minus 3, it will be less than c times x minus 3. So in other words, remember we said we need the absolute value of x squared minus 9 to be less than epsilon. And we said the absolute value of x squared minus 9 is the same thing as, x squared minus 9 is something x plus 3 times x minus 3. So it means actually the absolute value of x squared minus 9 can be simplified into the absolute value of x plus 3 times the absolute value of x minus 3. And we already said x plus 3 is less than c. So in other words, from what we have here, it means actually multiple of x plus 3 times absolute value of x plus 3 and x minus 3 will be less than c times x minus 3. I hope that part was clear. So in other words, it means actually, because remember that we need this part of the absolute value of x minus 3 so that we can be able to make sure that our delta is greater than that. So it makes sense for us to take this part of c times the absolute value of x minus 3 to be less than epsilon. So the delta that we choose, we can change it to be some epsilon over some number c, such that that number c is greater than absolute value of x plus 3. So basically it means actually from here, we can choose our delta to be epsilon over c. So I think we can choose to see if our choice was a good one. So remember, we're trying to find some smallest interval centered at 3, such that let's maybe take for an example. If absolute value of x minus 3 is less than 1, it means actually from here, remember that you're going to have x minus 3 is less than 1 and is greater than minus 1. So if we add plus 3 on both sides, on all sides, if we add 4 rather, what am I saying? We are adding 3. If we are adding 3 all out, same thing this side, you add 3. So obviously minus 3 plus 3 cancels, you're left with just x. 1 plus 3 is equals to 4. 3 minus 1 is equals to 2. So basically, it means actually we need for x minus 3 to be less than 1, we need x to be between 2 and 4. We can check that on a number line. If we choose a number line, let's say this part is 0, 1, 2, 3, and say 4, and okay, for argument's sake, let me put 5. So basically for x to be within a distance of 1 unit. So if 3 is here, so for distance to be less than 1, it means actually we need to choose numbers that are between 2 and 4, because you can see that this is not equals to, but if this was equals, then these brackets will to become square brackets. But because there's no equals to, it means actually the distance should be less than 1. So that's why around 3 here we have 4 and we have 1, and I said the distance should be between 4 and 3. So any value of x that you take between 2 and 4 and substitute it here, that distance will still be less than 1. So from here, from this x being between 2 and 4, if we add 3, right? If we add 3 throughout, 3, 3, we end up having x plus 3 is between 5 and 7. Right? So if that's the case, it means actually we can take that the absolute value of x plus 3 will be less than 7 from what we have here already. So if we make c to be 7, right? Remember that we trying to come back here. We said delta should be epsilon over c. So we want to see what value is appropriate for this c. So now we can say that c is equal to 7 is a suitable choice. So in other words, we have two restrictions on x minus 3. So x minus 3 is less than 1, like we did here. For us to have this x being between 2 and 4. And again, x minus 3 is less than epsilon over c, which is epsilon over 7. So because remember that we're talking about closeness, so we are trying to minimize the distance from 3 as much as we want, right? So meaning we can now take our delta to be a very minimum value between 1 and epsilon over 7. So after now that we choose our delta, so now we want to show that actually our choice is correct. So we are given some epsilon that is greater than 0, and we choose or we let delta to be a very minimum value between 1 and epsilon over 7. Remember, epsilon is not a specific number, but we know it to be a very small number. If this is the case, so it means that actually if absolute value of x minus 3 is less than epsilon, is less than delta, then we have so far from our choice of 1 and epsilon, it means actually x minus 3 is less than 1, or I'm sorry, the absolute value of x minus 3 is less than 1, or the absolute value of x minus 3 is less than delta. So from here, we remember that we added 3 all out, and that's when we had x is between 2 and 4, added 3 again, and we end up having 5, x plus 3, 4 plus 5. So it means actually the absolute value of x plus 3 will be less than 5. So in other words, going back to what we have, it means actually if we choose our delta to be epsilon of 3, if we have this absolute value of x minus 3 being less than delta, then absolute value of x squared minus 9, remember we can factorize x squared to be x plus 3, x minus 3, we can separate the absolute values. It means actually this from what we have here. Sorry about that part. I'm talking about what I have here. It means actually x plus 3 can be substituted by epsilon over 7. I hope that part is clear. So in this case, it means actually the absolute value of x minus 9 is less than epsilon. I hope that part is clear. So this is how we choose. From choosing the minimum between 1 and epsilon over 7, we get to prove, or we get to see that actually even trying to run away from it, it comes back. I want to stop here for today, but otherwise, remember we spoke about one-sided limits before. We spoke about vertical asymptotes and all those. So this precise definition of limits can also be used for one-sided limits. And for these notes, I wrote the notes on the left-hand limit and the right-hand limit to explain actually what we mean. Hope you go through them as slow as you can. So that even for one-sided limits, for us to be able to say that the limit exists or the limit is this specific number, we need a precise way of proving that. And that is what we just did right now. We just given a precise definition of of a limit. So I'm going to stop here. Remember, we're sharing the notes. You can read the notes on your own. And when you have the notes on your own, you can just read at whatever time that is suitable for you. I'll stop here and see you on the next lesson, talking about continuous function. What do we mean when we say a function is continuous? I'll stop here and continue enjoying the rest of your life.